The oceanographer had been staring at the same section of data for 40 minutes when her colleague walked into the room and asked what she was looking at. She did not answer immediately. She pointed at the screen instead, at a graph that showed the temperature profile of the water column at a specific location in the Central Pacific, the vertical distribution of warmth from the surface down to 800 meters depth, measured by an Argo float that had completed its profiling cycle and uploaded its data to the satellite relay network 4 hours earlier. Her colleague looked at the graph for a moment and then looked at it again more carefully, and she understood from the change in his expression that he was seeing the same thing she was seeing and reaching the same conclusion she had reached about what it meant. The temperature profile was wrong. Not instrument error wrong, not calibration drift wrong, not the kind of wrong that gets resolved by checking the sensor history and finding a deteriorating battery or a fouled intake port. It was wrong in the specific way that a physical measurement is wrong when the physical reality it is measuring has changed in a way that the observer was not expecting. The thermocline, the boundary between the warm surface layer and the cold, deep water that normally sits at a predictable depth in this part of the Pacific during this season, was deeper than it should have been. Not slightly deeper, not by the few tens of meters that normal interannual variability would account for. It was deeper by approximately 140 meters, compared to the climatological average for this location in this time of year. And the reading was not from a single float, but from every float in the surrounding array that had completed a profile in the past 48 hours. 17 floats spread across a region of approximately 300,000 square kilometers, all showing the same anomaly, all reporting that the warm water extended deeper into the ocean than it was supposed to. She had been working in oceanography for 19 years. She had processed Argo data through the 2015 to 2016 El Niño, through the record-breaking ocean temperatures of 2023, through multiple episodes of Pacific decadal variability that had generated their own anomalies in the float network's data stream. She knew what the strongest El Niño signals looked like in the subsurface temperature record. She knew what warm Kelvin waves looked like as they propagated eastward across the Pacific from the warm pool, carrying their thermal anomaly in the thermocline and delivering it to the eastern Pacific, where it drove the surface, warming that meteorologists tracked as the signature of El Niño at the ocean surface. She knew what all of the expected anomalies looked like, and what she was looking at was not any of them. The anomaly had the spatial scale and the coherence of a warm Kelvin wave, covering a large area with a consistent signal that argued against a local or random origin. But the depth of the thermocline depression, 140 meters below climatological average, exceeded anything she had in her personal experience of Argo data processing. It exceeded the largest thermocline deepening she could find in the ENSO literature for strong El Niño events. And it was located in a part of the Pacific where, based on the standard model of Kelvin wave dynamics, a warm anomaly of this magnitude was not expected to be at this point in the current ENSO cycle, which the official forecasting products were describing as a moderate La Nina transitioning toward neutral. She opened a second window and pulled up the sea surface height data from the satellite altimetry network, which provides an independent measurement of the ocean's thermal structure because warm water expands and the ocean surface rises above regions where the subsurface heat content is elevated. The sea surface height in the region of the Argo anomaly was elevated above the mean by an amount that was consistent with the thermocline deepening the floats were reporting. The two independent measurement systems were telling the same story, and the story was that there was more heat in the subsurface of the Central Pacific, concentrated in a specific layer in a specific region, than any of the operational models or the official monitoring products were currently accounting for. She sent a message to the NOAA Pacific Marine Environmental Laboratory at 6:47 in the evening. The message contained a link to the processed float data, a link to the altimetry product, and 2 sentences of her own assessment. The second sentence read, "I'm not sure this is a Kelvin wave. The Pacific Ocean is the dominant external driver of year-to-year climate variability on Earth, a role it exercises primarily through the El Niño Southern Oscillation, the coupled ocean-atmosphere system that redistributes heat and moisture across the tropics and subtropics and whose teleconnections reach into every corner of the global climate system. The ENSO cycle is driven by the sloshing of warm water back and forth across the Pacific Basin, the accumulation of warm water in the Western Pacific during La Nina conditions, and its eastward propagation toward South America during El Niño conditions, driven by and in turn driving the wind patterns that are the atmospheric component of the coupled system. The mechanisms of this sloshing have been studied for decades, and the theoretical framework for understanding the ocean dynamics involved is well developed, built on the physics of equatorial waves in a stratified ocean and the feedbacks between the wind field and the sea surface temperature that cause the system to oscillate. The Kelvin wave is the primary oceanic mechanism by which warm water anomalies propagate from the western Pacific to the eastern Pacific, and it is the structure in the subsurface thermocline whose behavior oceanographers watch most carefully when they are trying to anticipate the development and evolution of El Niño events. A warm Kelvin wave is an eastward propagating depression of the thermocline, a deepening of the warm-cold boundary that moves along the equator at a speed of approximately 2 to 3 meters per second, carrying its thermal anomaly across the full width of the Pacific in 2 to 3 months. When a warm Kelvin wave reaches the eastern Pacific, it deepens the thermocline there, suppressing the upwelling of cold water that normally keeps the eastern Pacific cool, and sea surface temperatures in the eastern Pacific rise. The sea surface temperature rise is what meteorologists detect as the surface signature of El Niño, but the subsurface Kelvin wave is the carrier of the heat that produces it. The standard monitoring products that track ENSO development use the characteristics of Kelvin waves in the subsurface thermocline as key indicators of the likely future trajectory of the ENSO system. The depth of the thermocline anomaly carried by a Kelvin wave, the warmth of the water in the depressed thermocline region, the width of the wave, and its meridional extent, and the timing and phasing of the wave relative to the ENSO cycle are all used to construct the forecasts that the operational seasonal prediction centers issue to guide the agricultural and water management decisions of governments and communities around the world. These forecasts have become progressively more skillful over the decades since the NSO monitoring system was established, and they provide valuable information about the likely character of the coming seasonal rainfall and temperature patterns in the regions most sensitive to NSO variability. The anomaly the oceanographer found in the Argo data does not fit within the standard Kelvin wave monitoring framework, not because Kelvin waves do not occur or because the physics of their propagation is wrong, but because the specific characteristics of the subsurface anomaly she is looking at are outside the range that the standard Kelvin wave models produce. A thermocline depression of 140 meters below climatological average is larger than any warm Kelvin wave on record in the monitoring data that extends back to the establishment of the systematic Argo network in the early 2000s. It is larger than the subsurface anomalies that accompanied the 2015 to 2016 El Niño, which was one of the strongest on record. It is larger than the anomalies that preceded the 1997 to 1998 event, whose subsurface signature is documented in the pre-Argo monitoring data that the legacy TAO mooring array provides going back to the late 1980s. And it is spatially extensive in a way that is consistent with a Kelvin wave. But that may indicate a different kind of subsurface structure, one that has accumulated heat over a longer period and from a broader range of source regions than the standard Kelvin wave mechanism involves. The question that the anomaly is raising is not simply how large the next El Niño event will be, though that question is of enormous practical importance for the billions of people whose agriculture and water resources and public health are affected by ENSO variability. The deeper question is whether the subsurface heat content of the Pacific has reached a level that the existing monitoring and forecasting systems were not designed to handle, and whether the dynamics of ENSO in the current state of the Pacific are still adequately described by the theoretical framework developed during the period when the baseline ocean temperature was lower than it is today. The Argo float network that detected the anomaly is one of the most significant technological developments in the history of ocean observation. Before Argo, the subsurface temperature structure of the Pacific was known primarily from the sparse measurements made by expendable bathythermographs dropped from ships of opportunity, supplemented by the moored buoy arrays of the TAO Triton network that provides continuous measurements at a limited number of fixed locations along the equatorial Pacific. The ship-based and mooring-based data provided useful information about ENSO dynamics, but was spatially sparse and temporally limited in ways that left large regions of the Pacific unobserved. Argo floats are autonomous profiling instruments that drift with the ocean currents, periodically descending to a depth of 2,000 meters and then ascending to the surface while measuring temperature and salinity throughout the water column. At the surface, they transmit their data via satellite and then descend again to repeat the cycle every 10 days. The global Argo array now encompasses approximately 4,000 active floats, distributed across all the world's oceans, providing a three-dimensional picture of the ocean's thermal and salinity structure that is updated continuously and that has no precedent in the history of ocean observation. The Argo data has already transformed the scientific understanding of several aspects of ocean behavior that were previously poorly constrained. The observation of ocean heat content changes in the deep ocean, below the depth of 2,000 meters, where the Argo float's profile has been substantially improved by the recent extension of the Argo program, to deep floats that descend to 4,000 meters, providing heat content measurements in the deep ocean that had been essentially unmeasured before. The subtropical mode waters, thick layers of uniform temperature water formed by intense winter cooling at mid-latitudes that subduct below the thermocline and carry their thermal anomalies with them as they circulate through the ocean interior, are now routinely mapped by the Argo network in ways that reveal their role in communicating heat between the ocean's surface and its interior on timescales of years to decades. The specific finding in the Central Pacific that the oceanographer identified is in a depth range that has been well covered by the standard Argo array, making the anomaly robust against the concern that it reflects a sampling artifact rather than a genuine physical signal. 17 floats reporting the same anomaly across a coherent spatial region is a statistical reality that is very difficult to attribute to instrument errors or calibration issues. And the agreement between the Argo thermal measurements and the sea surface height from satellite altimetry provides the independent verification that makes the finding compelling. The anomaly is real. What it represents in physical terms is the question that the investigation now underway is trying to answer. The comparison of the anomaly with the historical record of subsurface thermal anomalies in the Pacific is one of the most significant outputs of the initial analysis because it provides the context needed to assess whether the anomaly is truly unprecedented or whether it falls within the range of past variability. The comparison is complicated by the fact that the Argo network, which provides the most comprehensive subsurface data, has only been in global operation since approximately 2005, and the most complete global coverage was not achieved until approximately 2007. The period of reliable global Argo data is therefore approximately 17 years, which is a short baseline for assessing the frequency of unusual events in a system that operates on interannual to decadal timescales. The longer record that is available from the legacy TAO Triton mooring array, which has been providing continuous subsurface temperature measurements along the equatorial Pacific since the late 1980s, does not cover the location of the anomaly, but provides coverage along the equator that can be used to assess whether the equatorial subsurface has ever shown anomalies of this magnitude during the TAO observation period. The analysis of the TAO data for the past 3 decades shows that the anomaly exceeds all previous TAO documented subsurface thermal anomalies at comparable depths along the equatorial Pacific, confirming that what the Argo floats are reporting is genuinely outside the range of what the available observational record has captured before. This comparison with the observational record is important, but it carries a specific limitation that the research team is explicit about. The observational record for the subsurface Pacific is short, and the physical system whose behavior is being documented has been changing over the period of observation as the global ocean has absorbed heat from the enhanced greenhouse effect. A subsurface anomaly that is larger than any in the observational record could reflect either a genuinely unprecedented event in the natural variability of the ENSO system, or it could reflect the accumulated warming of the Pacific Basin over the past several decades that has elevated the baseline from which ENSO variability occurs. And that has made anomalies of this size achievable that would not have been achievable in a cooler ocean. Distinguishing between these two interpretations requires understanding whether the anomaly is sitting at the upper tail of the distribution of natural ENSO variability, or whether it reflects a shift in the distribution itself, a change in what the Pacific is capable of producing that is a consequence of the changing baseline rather than of unusual natural variability. The implications of the anomaly for the global weather patterns that ENSO variability drives are what the operational meteorological and climate forecasting community is most urgently trying to assess. The seasonal forecast centers that issue the El Niño and La Niña outlooks that governments and agricultural planners use to prepare for the consequences of ENSO variability have been running their models with the current subsurface conditions as input and examining the probability distributions of outcomes that the model ensembles produce. The results they are getting are broader than usual, with a wider spread of possible outcomes reflecting the unusual initial conditions, and they are producing a higher probability of outcomes at the extreme end of the distribution than routine ENSO forecasting scenarios produce. The specific regions whose agricultural and water resource planning is most dependent on accurate ENSO forecasts are tracking the situation closely. The agriculture ministries of the major grain-producing countries in South America, which experience some of the most direct and impactful ENSO teleconnections in the world, have been briefed on the unusual subsurface conditions and their potential implications for the coming seasonal rainfall. The water resource authorities in Australia, whose rainfall patterns are among the most strongly modulated by ENSO in any part of the world, are reviewing their reservoir management strategies in light of the potential for an unusually strong El Niño event in the coming months. The monsoon forecasting programs of the India Meteorological Department and the meteorological agencies of Southeast Asia, which serve agricultural planning for some of the most food-insecure regions in the world, are incorporating the unusual subsurface data into their seasonal outlooks with appropriate communication of the elevated uncertainty. The uncertainty is genuine and it is large. The physical models that the seasonal forecast centers use to predict ENSO evolution are calibrated against the historical record of ENSO events and may not perform optimally when the initial conditions are outside the range used for model calibration. The models are designed to simulate the dynamics of ENSO and the conditions that have prevailed during the calibration period, and those conditions included a Pacific that was, on average, cooler than the current Pacific by a margin that may be affecting the dynamics of the system in ways that the models do not fully capture. The forecast uncertainty that the models are producing reflects both the inherent unpredictability of the ENSO system, which involves chaotic atmospheric dynamics that limit forecast skill at lead times beyond a few months, and the structural uncertainty in the models themselves, which may be systematically biased in ways that are not apparent until the system is operated in conditions for which they were not designed. The communication of this uncertainty to the users of the seasonal forecasts has been one of the most carefully managed aspects of the community's response to the anomaly. The seasonal forecast centers have extensive experience with probabilistic communication of ENSO outlooks, having developed the formats and the language for expressing probabilistic forecasts over years of engagement with the agricultural and water management communities that use the forecasts. The specific challenge posed by the current situation is communicating an increase in uncertainty, a widening of the probability distribution that reflects not just the inherent forecast uncertainty, but also the unusual character of the initial conditions, in a way that is actionable for users who are accustomed to working with narrower forecast distributions. The scientific investigation that the anomaly has prompted is not confined to the operational, oceanographic, and meteorological community. The research oceanography community has been engaged from the early stages of the investigation, motivated both by the immediate practical significance of the anomaly and by the longer-term scientific questions it is raising about the dynamics of the Pacific and the relationship between ENSO variability and the longer-term changes in the Pacific's heat content. One of the most active threads of the investigation involves the question of where the heat in the anomaly came from. The standard mechanism for accumulating heat in the Pacific subsurface during the buildup to an El Niño event involves the deepening of the thermocline in the western Pacific during La Niña conditions, when the trade winds pile warm water into the western Pacific warm pool and deepen the thermocline there. This western Pacific heat accumulation is then released eastward as a Kelvin wave when the winds relax at the end of the La Niña period. The current anomaly is consistent with this mechanism in its general character, but the magnitude of the thermocline deepening exceeds what the standard model would predict from the current La Niña conditions, which have been moderate rather than extreme. The discrepancy between the expected and observed magnitude of the subsurface anomaly has led the research team to examine other potential contributions to the heat accumulation besides the standard La Niña mechanism. One contribution that the analysis has identified is the role of subtropical heat uptake, the process by which warm water is subducted from the ocean surface in the subtropics and carried into the subsurface interior, where it can contribute to thermocline heat content on timescales of years to decades. The subtropical mode waters that are formed each winter in the northern and southern subtropical Pacific have been anomalously warm for several years, reflecting the elevated sea surface temperatures that characterize the current state of the global ocean, and their subduction into the subsurface has been contributing warm water to the thermocline layer at rates that are higher than historical averages. The contribution of subtropical heat uptake to the current anomaly is difficult to quantify precisely because it requires tracking water masses as they circulate through the ocean interior over periods of years. But the analysis of the oxygen and salinity signatures of the water in the anomalous thermocline region suggests that a significant fraction of it has a subtropical origin rather than a purely equatorial origin. This finding is important because it means that the magnitude of the current subsurface anomaly is not simply a product of the current La Niña conditions, but reflects an accumulation of heat from a broader range of sources over a longer period, a reservoir of thermal energy that has been building in the Pacific subsurface as the global ocean has absorbed an increasing fraction of the Earth's energy imbalance over the past decade. If this interpretation is correct, the anomaly is not simply an unusually large Kelvin wave generated by an unusually strong La Niña event. It is the expression of a systematic change in the heat content of the Pacific subsurface that reflects the longer-term trajectory of the global ocean heat uptake. This distinction has significant implications for how the community should think about the future trajectory of ENSO variability. A one-time, unusually large Kelvin wave generated by a strong La Niña event would be expected to propagate eastward, drive an unusually strong El Niño, and then be followed by a return to near normal conditions as the heat is discharged from the eastern Pacific and the system relaxes. A systematic increase in the background heat content of the Pacific subsurface would be expected to elevate the baseline from which future ENSO events occur. potentially making future El Niño events stronger, more frequent, or both, and making future La Niña events shallower or shorter as the elevated subsurface heat content reduces the cold anomaly that La Niña conditions are associated with. The coral reef implications of the anomaly are among the most ecologically significant dimensions of the situation, and the reef science community has been monitoring the development of the subsurface anomaly with a level of concern that reflects the already precarious state of coral reefs globally after the severe bleaching events associated with the high ocean temperatures of recent years. Coral reefs are thermally sensitive ecosystems whose survival depends on sea surface temperatures remaining within a narrow range above and below the evolutionary optimum for the specific coral species involved. When sea surface temperatures exceed the thermal tolerance threshold by 1 to 2 degrees Celsius for a period of several weeks, corals bleach, expelling the symbiotic algae that provide most of their energy, and if the elevated temperatures persist, they die. The global ocean warming of recent decades has pushed sea surface temperatures in many reef regions close to the bleaching threshold, reducing the thermal buffer between the temperatures that reefs normally experience and the temperatures at which bleaching occurs. The consequence of this reduced buffer is that the same El Niño-driven temperature anomalies that drove bleaching at specific magnitudes in previous decades now drive bleaching at smaller magnitudes, because the elevated baseline means that smaller anomalies are needed to push temperatures over the bleaching threshold. The bleaching events associated with the 2015 to 2016 El Niño were more severe and more geographically extensive than those associated with the 1997 to 1998 El Niño, despite the fact that the two events were of comparable magnitude in terms of their sea surface temperature anomalies, precisely because the elevated baseline of 2015 to 2016 meant that the El Niño anomaly was being added to a higher starting point. If the subsurface anomaly in the Central Pacific develops into an El Niño event of the magnitude that the model ensembles are suggesting is possible, the sea surface temperatures in the reef regions of the Central and Western Pacific could exceed the bleaching threshold by margins that have not been observed in the modern reef monitoring record. The Great Barrier Reef, which experienced mass bleaching events in 2016, 2017, 2020, 2022, and 2024, has been suffering from a frequency of bleaching events that does not allow adequate recovery between episodes, and the prospect of another severe bleaching season associated with a strong El Niño is one that the reef science community is approaching with genuine alarm about the long-term viability of the reef under continued warming and ENSO stress. The Indian Ocean, which is thermally connected to the Pacific through the Indonesian through flow and through the teleconnection between Pacific ENSO events and Indian Ocean warming, is also at risk from the current subsurface anomaly. Indian Ocean temperatures have been running at record levels for several years, and the coral reefs of the Indian Ocean have been under sustained thermal stress. A Pacific El Niño event of the potential magnitude suggested by the anomaly would produce additional warming in the Indian Ocean through the positive Indian Ocean dipole pattern that typically accompanies Pacific El Niño events, and the combination of the current elevated baseline and the El Niño-driven anomaly could produce Indian Ocean temperatures that exceed anything in the available record. The oceanographer who first identified the anomaly is not a reef scientist or a monsoon researcher or an agricultural planner. She is a physical oceanographer trained in the dynamics of the ocean's interior, in the physics of the waves and the water masses, and the circulation patterns that distribute heat and salt and momentum through the vast volume of water that covers most of the planet's surface. Her expertise is in understanding the ocean as a physical system, and the anomaly she found is a physical signal in a physical system that she has been studying for 19 years. What she has found, in the months since she stared at the temperature profile and pointed at the screen, is that the physical signal is more complex and more significant than any she has previously encountered in her career, and that its complexity is not simply the complexity of an extreme event within a known range of behavior. It is the complexity of a system that is behaving differently from the way it has behaved in the observational record, in ways that may reflect the underlying change in the system state that has been occurring, as the global ocean has absorbed heat from the enhanced greenhouse effect over the past several decades. She has been careful in what she claims and what she does not claim. The data shows that the subsurface thermal anomaly is larger than anything in the observational record. The data shows that it has a spatial extent and a coherence that are consistent with a dynamically organized structure rather than a random fluctuation. The data shows that it cannot be explained by the current ENSO conditions alone and may require the contribution of subtropical heat uptake to account for its magnitude. These are the findings that the data supports, and she communicates them as findings, with the appropriate uncertainty and the appropriate acknowledgement of the gaps in the understanding that the current analysis has not yet filled. What she does not claim is a specific quantitative prediction of how the anomaly will evolve, because the models that would be needed to make such a prediction are operating in conditions outside their calibration range, and their skill in those conditions is genuinely uncertain. She does not claim a specific prediction of how strong the coming El Niño will be, because the range of outcomes that the model ensembles produce is wide, and the uncertainty is genuine rather than false modesty. And she does not claim that the anomaly represents a permanent change in the behavior of the Pacific ENSO system, because distinguishing between an extreme event in the tail of the natural variability distribution and a genuine shift in the distribution requires longer-term data than a single anomalous observation can provide. What she does say, and what she has been saying in the scientific communications and the briefings that have followed from her initial alert, is that what is happening beneath the Pacific right now is unusual, that the unusualness is large enough that it requires serious attention from the operational forecasting and hazard planning communities, and that the investigation needed to fully understand its significance is underway, but not complete. This is an honest and carefully calibrated communication of what the science knows and what it does not know, and it is what the communities that depend on the seasonal forecasts and the ENSO monitoring products deserve to hear. The Argo floats are still profiling. The 17 floats that first showed the anomaly have completed additional profiling cycles since the initial discovery, and the data from those cycles shows that the anomaly is persisting, that the thermocline depression has not substantially reduced over the weeks since the initial observation. New floats in adjacent sections of the network are beginning to show signals consistent with the eastward propagation of the anomaly, tracking the feature as it moves toward the eastern Pacific, where its surface expression will eventually become visible in the sea surface temperature record that the broader public and the operational forecast community have been watching for signs of a developing El Niño. The progression of the anomaly from the central Pacific subsurface to the eastern Pacific surface will be the next major development in the story that began when the temperature profile came back wrong and the oceanographers stared at it for 40 minutes before pointing at the screen. When that progression occurs, the full weight of the ENSO monitoring and forecasting apparatus will be brought to bear on the emerging signal, with all of the institutional infrastructure of operational seasonal prediction, from the meteorological agencies of the major Pacific Rim countries to the international agricultural and food security organizations that translate ENSO forecasts into planning decisions. But before that moment, in the gap between the unusual subsurface signal and the surface expression that will make its significance unmistakable to everyone watching, the scientists who found it and who are working to understand it are in the kind of liminal scientific space that the history of oceanography has repeatedly produced, and that has repeatedly turned out to be where the most important advances in understanding begin. The ocean has told them something. They are working to understand what it said. The data is still coming in. And what is happening beneath the Pacific right now, in the depths that most people never think about, and that the Argo floats visit every 10 days in their patient cycling through the dark, is unusual enough that the watching needs to be careful, and the listening needs to be close. The temperature profile came back wrong. In the 19 years she had been working with this data, she had seen many wrong profiles. This one was different. The instruments were not wrong. The ocean was.